I will write the expression for A1 So, I will straight away write the expression, please check whether it is true. Minus L 2L, 2L plus LD minus L inverse into R minus 2R minus 2R minus RD R. So, this is A1. Is this okay? And of course, U1. So, U1 is minus L 2L plus LD minus L inverse EA minus EB, EB minus EC minus VD. So, if I want A2 and U2, I should consider the second subinterval of this 2 and 3 valve conduction mode. So, if I take the second subinterval, then I have an equivalent circuit which just shows only those elements that conduct non-zero current. So, 2 and 3 valves conduct. So, this is valve 3, this is valve 2, and I have RD, LD and VD on the DC side. RL, RL. So, I have EB and EC, the two voltage sources in this. So, if I denote the DC side current by ID, the equation that I get by applying Kirchhoff's voltage law is, so there are two resistances with value R and one resistance RD. So, 2R plus RD into ID plus 2L plus LD into dID by dt plus VD is equal to EV minus EC. So, if I write this in the standard form, I have dID by dt on the left hand side and the remaining terms on the right hand side. So, I get A2 as minus 2R plus RD divided by 2L plus LD. I am straight away writing A2. So, A2 is nothing but the coefficient of ID when I write this equation in the standard form. See, the standard form is the derivative of the state variable on the left hand side, that is dID by dt on the left hand side, rest of the terms on the right hand side. And U2 is just the remaining term on the right hand side. So, that is EB minus EC minus VD divided by 2L plus LD. So, you have got everything except F and G. So, if I want F and G, then I have to relate state variables at the beginning of the first subinterval to the state variable at the end of the second subinterval. So, the two state variables are ID. So, what was the state variable in the first subinterval? ID and I1. Now, in the second subinterval, it is ID. Okay. So, this is the general equation. So, if I take x1, the first element of x1 is ID. So, what is ID at alpha by omega O? So, can I write it in terms of x2? So, how to write it in this form? Say, what I need to do is I have to write an expression for ID and I also have to write an expression for I1 at alpha by omega. No, no. So, how to get it in this form? Say here in this equation, x1 at alpha by omega O is nothing but ID at alpha by omega O, I1 at alpha by omega O. So, that is x1 at alpha by omega O, and x2 at alpha by omega O plus T1 is what? ID at alpha by omega O plus T1. Can I relate ID at alpha by omega O and ID at alpha by omega O plus T1? They are same. Why?
Because it's periodic.
Yeah, ID is periodic with the period T1. See, ID is a DC side current. So, the period of ID is T1. So, ID at alpha by omega O is same as ID at alpha by omega O plus T1. Okay. Then, what about I1 at alpha by omega O? Okay. Now, can I relate I1 at alpha by omega O and ID at alpha by omega O? I mean, why one should do this becomes clear shortly. Can I relate these two?
So both are equal.
Hmm?
At alpha by omega 0, I3 is 0.
So, I3 is 0. So, they are equal, right? They are equal. See, alpha by omega O is the instant at which 3 is turned on. So, just before 3 is turned on, I1 and ID are same. So, just at the instant of turning on, I3 is 0. So, I1 is equal to ID. Now, from the previous equation, this is also equal to ID at alpha by omega O plus T1. So, from this, can I get F and G? So, from this, I get F and G. Both are of size 2 cross 1. So, what is F, what is G? F is 1 1, G is, so G was actually not required in this case. Now, why I use G is, that is a general solution. So, there are cases where G is non-zero. So, that is why we need that G. So, for this case G is actually not required at all because it is 0. Okay. So, this is as far as 2 and 3 valve conduction mode is concerned. So, if this is clear, we will move on to, say essentially we are trying to find x1, x2, a1, u1, a2, u2, f and g, that is all. So, given any circuit, if I know these things, I can go ahead and solve the equation, get the lowercase t1 and the solution. Okay. So, the solution can be obtained in a closed form. So, we have an expression for the solution, but that requires the knowledge of t1, the lowercase t1. So, that one can get only by solving a nonlinear algebraic equation. Okay. If this is clear, then we will consider the same circuit, but 3 and 4 valve conduction mode. So, again what we will first do is try to take the first subinterval and draw an equivalent circuit showing only those elements that conduct non-zero current. So, there is one loop current ID flowing through RD, LD, VD, and we consider one of the elements of X1 as the current through the outgoing valve, that is I6. So, I6 becomes 0 at the end of the first subinterval. And of course, the other current that I consider as a state variable is I1. So, the current through valve 3 is ID minus I1, and the current through EB is, okay, suppose I showed this in this direction. So, it is I6 minus ID plus I1. So, there are 3 loops and I have to apply Kirchhoff's voltage law to these 3 loops. So, x1 is the state vector for the first subinterval. So, I have to take I6 as the last element of x1. So, the other 2 elements of x1 are ID and I1, ID and I1. So, this also gives x2 straight away. So, x2 is same as x1 without the last element, that is ID I1. Of course, x2 is applicable for the second subinterval. So, let us apply the Kirchhoff's voltage law to the 3 loops. The first loop consisting of EA, EB, R, L and the valves 1 and 3. So, it is R I1 plus L d I1 by dt plus L d by dt of I6 minus ID plus I1 plus R I6 minus ID plus I1. So, this is equal to EA minus EB. That is the first equation. Now, if I apply Kirchhoff's voltage law to the loop consisting of EB, EC, RL and the valves 2 and 6, then R into I6 minus ID plus I1 sorry.
ID minus I1. You are going to equal to EC minus EB.
Okay, you want, okay, okay, I will go in this direction, fine.
Okay.
Then this is minus L d by dt of I6 minus ID plus I1. So, if I take the current through valve 2, it is I6, ID minus I6 plus L d by dt of ID minus I6 plus R ID minus I6. So, this is equal to EB minus EC. Then there is one more loop consisting of these valves 3, 6, RD, LD, VD. So, by Kirchhoff's voltage law, RD ID plus LD dID by dt is equal to VD, is equal to in fact minus VD. So, I will leave it to you to write these equations in the standard form. See, I will repeat what is standard form. Standard form of the first order differential equations. See, all these are first order differential equations. So, in the standard form, we get the derivative of the state variables on the left hand side, the remaining terms on the right hand side. So, from that I get A1 and U1. So, I will straight away give the answer. So, please verify that A1 is minus L 2L, L, 2L, minus L, minus 2L, LD, 0, 0. Inverse into A1 is of size 3 by 3, R minus 2R minus R minus 2R, R 2R and minus RD 0, 0. This is A1 and U1 is the same first factor that is appearing in A1, that is minus L, 2L, L, 2L minus L minus 2L, LD 0, 0 inverse into EA minus EB, EB minus EC minus V. Now, this is for the first subinterval. If I want the second subinterval, should I again try to get the equations or I have already got this? See, the second subinterval is nothing but the first subinterval of 2 and 3 valve conduction mode. So, I have already got x2 is already written. What is A2 and what is U2? So, A2 is equal to A1 which was obtained for first subinterval of 2 and 3 valve conduction mode. Similarly, U2 is nothing but the U1 for the first subinterval of 2 and 3 valve conduction mode. So, the only things that remain are finding F and G. So, if I go by the general equation, x1 at alpha by omega O is equal to F into x2 alpha by omega O plus T1 plus G. So, now we have x1. What is x1 at alpha by omega O? So, it is ID at alpha by omega O I1 at alpha by omega O and I6 at alpha by omega O. And the first term on the right hand side as x2 at alpha by omega O plus T1. So, this is ID at alpha by omega O plus T1 and I1 at alpha by omega O plus T1. So, to get F and G, what I should do is take one element of x1 at a time and try to get some relations. So, based on what happened in the first subinterval, can I say that ID at alpha by omega O, say based on what happened in the 2 and 3 valve conduction mode. So, what is ID at alpha by omega O? Yeah, ID at alpha by omega O plus T1, because ID is periodic with T1. Then the second element of x1 is I1 at alpha by omega O. So, that is again ID at alpha by omega O. So, which is nothing but ID at alpha by omega O plus T1. Then finally, I6 at alpha by omega O. So, what should this be? What is I6 at alpha? Huh? I6 is 0 at alpha by omega. It is not into I1 at. So, see I1 and I6 are identical except for a phase shift of 60 degrees, which is nothing but T1. Okay. So, it is I1 at alpha by omega O plus T1. So, from these three equations, can I say what is F? What is the size of F? 3 cross size of F? 3 cross 2, 3 cross 2. So, first row, what are the elements? 1 0, second row 1 0, third row 0 1. So, we get everything in the first term itself. So, again when you look at G, what is the size of G? 3 cross 1. Size of G is same as x1. So, it is same as the size of x1 and all elements are 0. This general solution is something which will be very helpful, and of course, one has to use a computer to solve for T1, otherwise calculator cannot be used for solution of such nonlinear equations. But there is, before using the computer, there is one integration that you have to do manually. Please note, there is an integration. So, if you recall, in the solution for the scalar T1 lowercase t with a subscript 1, there is a nonlinear equation involving an integral. So, only after simplifying this integral you can solve the nonlinear equation. Now, how to do that integration? See, if that integration will involve u1 and u2. See, if you look at u1, now in general this u1 depends on what is there on the DC side and what is there on the AC side. Now, on the AC side what you have is only sinusoidal voltage sources. On the DC side you have either a constant current source or a constant voltage source. So, if you look at all the cases that we have considered so far, whether it is u1 or u2, it is dependent on some constant or sinusoidal terms. Constant can be due to the DC side voltage source, and the sinusoidal quantity can be due to the AC side voltage source. Can I say that it is sum of 3 column vectors, where the first column vector is say L1, which is having the same size as u1. Okay, let me say K1, which is having the same size of as u1. Then L1 cos omega ot plus M1 sin omega ot. In general, say many times you come across these expressions in terms of EA, EB, EC. So, you have this sin omega ot plus some angle 150, 90, 150, 30, minus 90. So, in general this can be written as sin omega ot cos phi plus cos omega ot sin phi, where this cos phi and sin phi are constant because phi is a constant, but the other terms, other factors sin omega ot, cos omega ot are functions of time. So, what I am trying to say is I can in general write u1 as a constant plus a constant factor times cos omega ot plus a constant factor times sin omega ot. Can I do that? Because I will get terms like sin omega ot plus phi. Of course, there is a coefficient to that which is a constant. So, that gets absorbed in this L1 and M1. So, size of K1 or L1 or M1 is same as that of U1. Okay. So, K1, L1, M1. So, if I take K1, so if I take either U1 or K1 or L1 or M1, what is the size? What is the size of these? It is same as x1, which is nothing but n plus 1 cross 1. Size of x1 is n plus 1. We used the notation n for the size of x2. Okay. So, is this clear? So, these are all constants. K1, L1, M1 are constants. They are constant column vectors. Similarly, if you take U2, it can be written as K2 plus L2 cos omega O2 omega OT plus M2 sin omega OT. So, again here the size of U2, K2, L2 and M2 are n cross 1. they are column vectors, and k2, L2 and M2 are constants. So, when you look at that equation, nonlinear equation which has to be solved for that scalar t1, there are integrals of the type exponential of minus a tau u1, say there you come across this type of integral, exponential minus a1 tau u1 of tau d tau, exponential of minus a2 tau u2 of tau d tau being integrated. So, these are the integrals that you come across.